I'm gonna show you a little bit more about the work that we did on the global flood awareness system. What flood forecast information do we provide at the moment? We have a forecast frequency which is updated daily, so every day, once a day, we update our flood forecast. We go up to 30 days. Currently, the only variable we are forecasting obviously is river flow, so no water levels at the moment. We look at probabilistic information because, and I'll come back to that in a second, once you go beyond the first few days, you need probabilistic information in order to be able to make meaningful forecasts, but I'll explain that in a bit. And we have our temporary resolution of the forecast is daily. Now, let's look at the GloFAS model setup. As I said, one of our core principles is to use probabilistic forecast, and for a probabilistic river flow forecast, you need a ensemble system. So you need a probabilistic weather forecast. What are we doing? What are we using therefore? We are using the European Center for Medium Range Weather Forecast. I think that's probably the equivalent is the GFS in the US. They have ensemble meteorological forecasts. This ensemble consists out of 51 ensemble members, and it has a 15-day forecast horizon. So 15 days in advance, it forecasts the weather conditions. Now, I just said in the slide before, we have a 30-day forecast for river flowing. You might say, well, wait a second, if you only have 15 days weather forecast, how do you get to 30 days? Now, the trick is that when you are talking about very big river basins, the Mississippi, for example, the Amazonas, the Mekong River Basin, the Danube, at a certain point in time, actually, you only need to route down the water that is coming from an upstream precipitation event. Because what usually happens is that in those big river basins is that when you have in a certain part of the river a very big precipitation event, you can have skill in the forecast, even though beyond your weather prediction, because you just move the water downstream basically. Now that obviously works only in very large river basins, but when it comes to very large scale flooding events, that is remember for example Afghanistan, or Pakistan, or I think it was, I'm not sure if Afghanistan or Pakistan, which was a few years ago. That was such a very big event where routing the water down gave you additional information even beyond the next 15 days. Now, what's the spatial resolution of these forecasts? We have roughly 32 by 32 kilometers for the first 10 days, and then the spatial resolution grows. It goes to 65 by 65 kilometer grid cells for days 11 to 15. Now I said, why do we actually use probabilistic forecasting? I'm not sure how much you know about probabilistic forecasting, but just some very basics. You know that weather forecasts are always uncertain, and the further you go into the future, the more uncertain are those weather forecasts. But there's a trick. We can stretch, let's say, the limit of predictability a little bit if we don't look at a single weather forecast, but we look at many different possible outcomes of equally likely weather simulations for the future. So with ensemble system, we are able to stretch, let's say, the limit of predictability a little bit further into the future. But remember, when we are talking about probabilistic forecasting, remember that in ensemble predictions, a priori, each single member of the ensemble is equally likely. So it's not that there is one member more likely than the other. And although we have 51 ensemble members in our case, and they are designed to capture the variety of possibilities in the future, the truth may not always be captured. Okay, So even then, it's possible that if an event is so extreme that you are not able to capture it with the weather forecast. And obviously, it's also clear, but I'm sure you know that obviously uncertainties in the errors grow with time in your forecast. Now, those ensemble weather predictions will stick into a cascade of hydrological models. That cascade consists of of a land surface scheme, which is called HTESL, Hydrology Tiled ECMWF Scheme for Surface Exchange over Land. Very long name. To make it short, what it does, it calculates, as I wrote here, the surface heat and evaporation and the soil water budget. What you get out of that model is basically a surface, two variables, that is surface flux and subsurface flux for each grid cell in the land surface scheme. Now those again we take and we stick them into a routing model, and actually a little bit of an extended routing model, which is called ListFlood. ListFlood is actually a full rainfall runoff model, but for that purpose we have stripped it down to only include groundwater and the routing processes. And what it does is simply uses a drainage networks with a global runoff network with channel characteristics and routes these fluxes down into the sea. And the output of that is a daily river discharge that you can see in GloFAS at 0.1 degree spatial resolution. Now there's an article about that, and if you really want to have all the scientific details about how this works, then you should look it up in hydrology Earth System Science. The reference is down there, but I'm sure Jim can give you the detailed reference after this presentation. Now, I see that I'm missing a slide. Now, no, here, sorry. Now, what are the advantages of such a setup? Why didn't we set up an entire model, rainfall runoff model ourselves? Well, the advantage is very simple. HTESL is part of the operational procedure at the ECMWF, so at an operational weather forecasting center, and that makes it easy, obviously, for us to maintain and to keep it running, rather than us having to set up the entire rainfall runoff system. It also reduces enormously the amount of data that we need to put in. As you've seen, we basically only take the two output files that come out of this HTESL model and stick it into our routing model in order to produce then some flood forecast. Now, disadvantages is obviously that once you want to start calibrating the system, it's very difficult because in theory you need to calibrate both models. That's obviously very difficult because HTESL is designed to provide atmospheric feedback into the numerical weather prediction and not to have nice fluxes for river routing. But in future we hope that that's a benefit then for the weather prediction system in order to calibrate also for let's say river runoff. Now, let's say we have this, and I need to speed up here. We have, let's say, our river discharge forecast. So you have a map with pixels, and you click on one of the pixels, and it says, whatever, 5,500 cubic meters per second in the next days of river discharge. The question is, because it's a global system, how do you know how severe that river discharge is? In the Amazonas, 5,500 cubic meters is probably nothing, whereas in some river in a semi-arid area, this might be a 500-year flood. Okay. Now the question is, how are we able to classify or to quantify these discharge forecasts? Now we use a trick here. And what we do is we run the entire model setup that I've just presented through a long-term climatology. We use in this case a global reanalysis data set. It's called ERA Interim. A reanalysis data set is basically a data set that comes from a weather forecasting model that has been run for the past. Okay, we stick that into our HTESL list flood combination, and with that we get basically a simulated discharge time series for each model grid pixel, okay, like it's shown here. Now, on that time series, obviously, and I'm sure you've done that, you can do return period statistics. So for each and every pixel in the model, you can get out, let's say, the river of the discharge value, which represents a certain return period. And this is what you then see in the end in GloFAS. One of these graphs here, I've just taken one example graphs, but on the left-hand side on the left axis, you see that it is showing the calculated return periods. On the right-hand side, you see the actually simulated discharges. So that right away enables the user, even though he may not be familiar with the river flow characteristics in that specific river basin, to quantify how much or how potentially dangerous this flood forecast is. So another advantage of such a system is that because you compare return periods that come out of a model climatology, you eliminate also systematic bias that you have in the model. So let's say you have a systematic over or underestimation in a certain section because your processes are not well represented or for whatever reason, but because you compare modeled forecast discharges with modeled return periods, you are eliminating those, or at least partially eliminating those systematic biases. Again, it's also easily understandable for different users. Return periods usually everyone understands and can also be linked then more to national levels. So also for the national end user, then this might be an easier way to connect GloFAS forecast with his own information. Now, let's quickly go through because we're already past or at the half hour. So I'm just going to quickly go through a few slides which show what updates we are planning with GloFAS. One of the updates that we have foreseen within the next month actually is the incorporation of major lakes and reservoirs and stream flow evaporation. What do I mean with that? Well, currently the setup as you see it in GloFAS right now ignores lakes and reservoirs. Now you might say, well, that makes the model pretty not trustable because lakes and reservoirs have a huge influence. True, that's absolutely correct. Now, however, we are talking about a global hydrological model, so incorporating lakes and reservoirs is not something that you do in a few hours, because we are talking about thousands of lakes and thousands of reservoirs. Now, what we did here is, as you've seen, we will incorporate the biggest world lakes. We've selected 463, and the biggest reservoirs. So in total, we have 1,100 lakes and reservoirs in the future in GloFAS, which is still far below what is actually out there. But when you do global modeling, that's the trade-off you have to make. We also, at the moment, the current setup of list flood doesn't simulate evaporation loss from the riverbed. We do evaporate water, let's say, from the normal surface in the land surface scheme, but let's say the evaporation from the actual river stream is not included. And that can obviously in the tropics be very important, so that's why we have included this now, and will hopefully come with that update within 1 or 2 months. In the picture actually below, you see when we compare against observations, the green points basically show where the mass subcliff improves, and the yellow where it actually gets slightly worse. And all the gray stations show that the impact of incorporating these lakes and reservoirs, at least for those stations, seems to be almost not noticeable. So you see, even though we incorporate a hydrologic feeder which should in theory improve everything, not necessarily that's always the case. Another planned update is the use of reforecast. Very quickly, what is a reforecast? Instead of a reanalysis, a reforecast is a retrospective run of the actual weather prediction model for the last 20 years. When you compare it to a reanalysis dataset, a reanalysis dataset is in a sense the same thing. The only thing is it was run many years ago, in this case at 2006, and the weather models in between have improved from 2006 until 2015. There has been many updates made. So we are comparing the return periods that we use from a reanalysis product, which was from an old model, with the weather forecasts, which are from a more updated model version. So there's some inconsistency there, and reforecasts are a way to overcome that. Now that is actually shown also here in that graph. You see that we have compared this, the skills there. I can't go in detail here. There's a paper that has been submitted to Journal of Hydrometeorology and is currently under review. Once it's published, I'm happy to share that. But it shows basically that using reforecasts, our forecast skill improves for the first few days, whereas for the last days, it's more or less the same. One last thing before I come to an end. I said we only have currently river flow forecasts, but many of our end users actually want impact. So they want to know, well, how many people will be affected, or which major city will be flooded. So we need water levels, and for that we don't actually only need water levels, we actually need flood inundation maps. And what we did here is we developed a global flood hazard map that we are linking now using a kind of a library approach with the GloFAS forecast. So we can we're able to make predictions also with regard to how many people would potentially be affected and how many cities would be flooded, or how many agricultural land, etc., etc. At least we would be able to give rough numbers. There's also 2 articles on that under preparation. We are about to submit them, but I can't give more details yet on that. But that's something for next year that we've foreseen for next year. And then, of course, we are trying to look at different features for the web interface. They have not so much to do with science, or with hydrology. They're more making the end user experience nicer. So there will be a sales search function, a layer transparency. We'll have a feature that enables you to add web map services from other web map services. So you could, for example, add when you have your setup with Tessis, I hope you will add some of the outputs. You could add that to GloFAS and compare. And last but not least, we're also trying to set up a GloFAS sensor observation service where you can actually get for some real data stations GloFAS forecast.